nobody wakes up in the morning wanting to dry.
Sure.
Okay,
Absolutely.
this is not on their top 10 list. What we're trying to assure is not just a pellet dryness at the end of the run, because frankly, if they have to measure it and they find that it's not right, it's too late.
There's a lot of differences between, what your blower might say it can perform, and then what is the air actually doing once it gets to the hopper. That inlet tube becomes so important. Sometimes there's drawbacks and there's hindrances when you do certain things.
Sure.
Certain decisions have certain consequences, pluses or minuses.
Sure.
And so I think that's definitely been the biggest takeaway when you visit these plants, is that everyone's doing their own thing. And there's a little bit of black magic in it all.
There's a lot of black. And speaking of black magic, I mean, you've been in the drying area for the last how many years, and that's just seems to be full of black magic. And some of what you're doing is try to take some of that black magic away and put some
science behind it,
solid science behind it, right?
Yes. And I mean, that's one of the benefits of the tools, I think.
So tell us about those tools a little bit.
Yeah, so as Greg was mentioning, we use ANSYS Fluent and Rocky. And Fluent is the CFD, so computational fluid dynamics, which is mainly looking at the air, specifically for us, the air. Now, you can make that whatever fluid you want. If you were doing nitrogen drying, you can do all different gases, all sorts of things. But for us, it's mainly air. And that has been beneficial in looking at, there's a lot of differences between, what your blower might say it can perform, and then what is the air actually doing once it gets to the hopper. That inlet tube becomes so important. That's one of the first things when we were going through this. I was like, hey, what is the meters per second, right here? And there's not there wasn't a clear answer for it.
Sure.
So, luckily Kevin, our lab manager, and here in our lab, we're able to break things apart and measure those sorts of things. But then it also goes inside the hopper, and it allows us to look at the airflow inside the hopper, which is a really complicated place to be.
A great dynamic tool. You're seeing things in a dynamic fashion, right? Yeah.
And then ANSYS Rocky, which is one of their newer platforms. I would say Fluent is probably their gold standard product.
Yep.
Rocky is one of their newer ones, which does DEM, which is discrete element method, which can do a lot of different things. It can look at how bottles are going down a line. It can do all sorts of particle sort of simulation work. But for us, mainly we're using it for the resin itself. And what's great about the tools is you can use them separately. So you can use Rocky just to look at resin flow, because one of the big things in our industry is whatever's coming in at time X, you want it to be coming out together at time Y.
Good mass flow in a hopper.
Yes, exactly. We don't want mixture going on in there, vertically.
Because the particles get different exposure times
Yes,
in, right?
which is going to make our situation even harder than it is.
4 to 6 hours. I mean, we're talking about hours, hours of time, and I guess it depends whether you're a 4-hour person or a 6-hour person. Are you optimistic or not so optimistic?
And if you're going to have to guess, you're usually going to guess on the safe side. So you're always going to go longer than probably you need to try and be safe, right?
So it's I think part of the selling pitch to me, because we invested in this 2 years ago now, 3 years ago.
Yep.
And
Significant investment,
significant, 6 figures investment. And we just added to it some more as well, some other packages as well, because we're using it on the other conveying packages right now.
The sound and so forth,
But so, I mean, how from, I guess it took you a while just to wade into learn this package.
You got to learn the
get
tool,
into
right?
it. Yep, for sure.
Right, yeah.
And we've had great partners. They've been really helpful in teaching. There's a learning curve for sure. And it's not necessarily, you can learn a whole bunch of stuff in college, but the applications in industry sometimes differ than just the straight up equations. In
Sure,
college.
of
In college, you never imagined that you're going to be modeling a bunch of dryers, right?
No, not really.
I mean, when you go out to the bar and you describe what you're doing, I mean, not many of your friends are going to understand that.
No, but it's the tools. There's a lot of benefits to the tools from just what can we look at? What areas can we look at? How can we focus in? And a lot of that has to do with, as I'm sure we'll get into later, like just looking at hopper geometries, changing different things, changing bends, elbows, lengths, perfs, what's 1 inch here versus 2 inches there. Like all those things we can see through the software, pretty substantial changes, as opposed to just, while it is our ultimate goal and it is the most important thing of providing dry plastic resin for our customers, there's a lot of different, levers that you can pull in order to get to that. And sometimes those levers aren't seen in just the simple, did you reach 200 parts per million?
It's got to be more anticipatory, right?
Yeah, exactly.
Based on the information.
But even more so is the uniformity of that drying process.
Sure.
And a lot of the decisions that get made along the way by various people in this industry dictate that uniformity across that hopper. So that's what we model. So the modeling that Joshua works on then gets validated in the lab with the sizes of the machines we have
exactly.
here. And then
Hugely
we can
important.
extend it and scale it and do make the tests that are appropriate, as you talked about.
Yeah, well, I think that's an important point. That's very, very valid in explaining what we're doing here. Is you're doing a lot of the computational and the theory and proving theories and disproving theories, but then you get your hands dirty. You get over here and you load drying hoppers and you crawl inside machines, and you and Kevin do a lot of hands-on stuff. And that's, I think, an important distinction, an important difference is that the theory is vitally important for our understanding of why, but that dirty hands proving point, and that's been really, really good and very important for the way we're approaching this.
And I think that's ultimately like we were saying, what is ultimately the most valuable asset is uniform, consistent, dry resin. And that is what we're shooting for. And like we were saying, there's a million different levers that you can pull and how you can get there. Some of them are dictated by the physics of it all. We can't just melt the plastic, but there are decisions that you can make along the way to get to that, for better or for worse,
so
or
you can adjust in
more
process,
efficiently, more efficiently or less efficiently. And so I think with the ultimate idea of hey, we're going to try and make consistent dry resin, it is important to validate that step and do it with our stuff and see, the prototypes, we're prototyping things right now that we're going to try and implement. There's a lot of differences between, what your blower might say it can perform and then what is the air actually doing once it gets to the hopper. That inlet tube becomes so important. That's one of the first things when we were going through this, I was like, hey, what is the meters per second, right here? And there's not there wasn't a clear answer for it.
Sure.
So, luckily Kevin, our lab manager, and here in our lab, we're able to break things apart and measure those sorts of things. But then it also goes inside the hopper, and it allows us to look at the airflow inside the hopper, which is a really complicated place to be.
A great dynamic tool. You're seeing things in a dynamic fashion, right? Yeah.
And then ANSYS Rocky, which is one of their newer platforms. I would say Fluent is probably their gold standard product. Yep. Rocky is one of their newer ones, which does DEM, which is discrete element method, which can do a lot of different things. It can look at how bottles are going down a line. It can do all sorts of particle sort of simulation work. But for us, mainly we're using it for the resin itself. And what's great about the tools is you can use them separately. So you can use Rocky just to look at resin flow, because one of the big things in our industry is whatever's coming in at time X, you want it to be coming out together at time Y.
Good mass flow in a hopper.
Yes, exactly. We don't want mixture going on in there, vertically.
Because the particles get different exposure times
Yes,
in, right?
which is going to make our situation even harder than
Sure.
it is. We can also look at the fluent side, which, like I was saying, the airflow, how it's distributed in the hopper, the actual speeds, and then you can merge them together where they couple together and they piggyback off of one
And then
another.
you find out how they interact. in
And
that
exactly,
process. Okay.
and the calculations work together where they basically ping pong back and forth, which takes a little bit more time, but it gives you a really in-depth look into how is the heat transfer working in different parts. How does, when you move, as the particles are moving through the bed, how is that interacting with the air now? How are those changing? And so you can get into some pretty interesting aspects with these tools that I would say are pretty difficult to measure in the field. It's hard to pick up a couple of meters per second within a packed bed with resin
Sure,
around
yeah.
it.
I mean,
So
It's a difficult situation. You got this packed bed of, thousands of pellets, and they're not always uniform pellets. You've got reclaim mixed in there. Sometimes the bulk density is a little bit mysterious and not always entered properly. You got all these things going on, and certainly I think what we're trying to do is use these tools to be able to better understand what goes on inside, rather than having this wild ass guesstimate of 2 to 4 hours or 4 to 6 hours. I mean, we're talking about hours, hours of time. And I guess it depends whether you're a 4-hour person or a 6-hour person. Are you optimistic or not so optimistic?
And if you're going to have to guess, you're usually going to guess on the safe side. So you're always going to go longer than
Right.
probably you need to try and be safe, right?
To the novice person, and probably to many of our customers, they walk down the aisle at the show and they look at a dryer. Well, it's a box, it's a hopper. They all look the same, but they really aren't when we go and test them.
yeah, and there's little differences in all of them, and those little differences add up in a way, or sometimes they cancel each other out.
Sure,
So,
Right.
Well, I think people get enamored by the typical American stuff, horsepower, right? So how much CFM is there, and how much KW
But
is...
even CFM,
But
nobody measures it
Which
the same
CFM,
way.
yeah.
But that's part of the problem. And it goes beyond that. So like, let's say that every dryer is producing 100 CFM. And so we're like, okay, everybody's equal. But then to your point, Joshua,
What's
what we
getting
were
to the
talking
pellet?
about is how is that being delivered,
Right.
right?
What's getting to the
It's
pellet?
what size is the inlet? Is it a mitered? Is it a sweep? Is there a bell? How much perforation?
Yeah,
What position
absolutely.
is it in?
what percent perf?
Yeah,
what
I mean,
angles?
And we've seen what the impact of each of those decisions and people's designs has on the drying process.
And the pressure drop
yeah.
across
Yeah.
the beds. I mean,
I think it is an extremely important and valid point to make as well, because Connor, you mentioned, we not only have Novatec dryers in our lab, we have everybody's dryers in our lab. We've gone to the trouble of trying to acquire these, through various entities out in the field, and it's important to note that Josh and Kevin do not go into. We don't give them any preconceived notions on the. We're not going in there to prove Novatec's dryer works better than dryer X or dryer Y or dryer Z.
The four things are heat, airflow, time, and dew point. Those are the four things. And within those four things, there's kind of sections off of it. So
Subcategories, right,
subcategories or how to think about them. So the way I like to think about heat, which in my opinion is the overarching most important one, and Mark talks about this as well. Like you can have minus 40 all you want going into your hopper. It's going to take 24 hours, if not ever, to dry.
Because you don't excite the water
Yes,
molecules, right? And I've
we've-
heard the molecule story. You know?
Yes. So we got to have heat in there.
Sure,
And
absolutely.
heat is tricky because we obviously can't melt the plastic, but we want as much of it as we can. And so we kind of, that's the whole premise of the whole drying temperature. So you get up close to that point, but just below it. So you're exciting the molecules, you get everything moving, but you're not melting it. And that comes from the air temperature. That's typically what we're measuring. But through a lot of our simulation work, and even I'm sure people in the industry would understand, it's not instantaneous. There's a time aspect even to the heating. So in these typical Lance style diffusers, or even the cone ones in the much larger hoppers, the heat is going to be concentrated in the bottom at the beginning. And then it is going to essentially percolate up as the lower resin is heated up. So, if you're drying at 180, you essentially have to wait for the bottom layers to reach 180 before the air can be 180, because at that point it's at
It's
equilibrium.
absorbing BTUs as
Yes,
it's heating, right?
and
Yeah.
so they're equal, and then it's going to creep up the hopper. And so that whole process takes time. But it becomes important to note the difference between the air temperature and the actual resin temperature over the course of the drying period. And I think Novatec has done some very clever things kind of measuring this, are measuring the differential between the inlet and the outlet, and then ramping back over time if it's not in use. Like, we've done some really clever things to save energy and save power related to this whole concept of resin temp. And then the next one, airflow, which through even some of the simulation work, we'd like to expand that. It's delivered airflow. There's...
What do you mean by
Yeah, I love
delivered?
that
So-
distinction.
Delivered where?
So the critical point is going to be when we say delivered, the actual airflow going into the hopper. And so typically we like to measure that right at the inlet. We have our whole system in the lab to measure that. And the key is there is a lot of different factors over the course of even the piping, the routing, whether you're using a bed or a cassette or how you're doing it, that can kind of change what you think might be your CFM to what
Because
is...
those points all create losses, right?
Yes,
Yeah.
exactly. And so it's important to understand what your actual delivered airflow is, because the delivered airflow is what is really going to drive a lot of what falls into this category of packed bed flow, which is essentially what we're doing. And that drives a lot of the thermodynamics and the physics of the actual system. And so, and it sounds crazy, but there are big differences, or what can be noticeable differences, between minimal CFM differences because of how all of the math appears to work out, which has definitely been interesting. I think sometimes it's like, oh yeah, it kind of bounces around here. Maybe it's some days it's 70, some days it's 65, but like you gotta try and drive to what is your delivered airflow. And I think that's actually one thing in our central systems that we do great, our HB units. Because, the HB, the heater blower, is hooked right there at the inlet. Like, you are going to get the airflow.
You're getting what the intended is.
Yes.
Right.
And so I think that's a great design application that we have already. But
Basically a booster for the desiccated airflow that
Yes.
you have going
Exactly.
through, on central drying.
yes. And then next into the airflow, so it is that ultimate CFM in, but then there's the uniformity aspect, and then ultimately the velocity of the air. And so we like to talk a lot about CFM because it has to do with the BTUs and the heat transfer and kind of this volume idea. But in a lot of the equations, it ultimately boils down to what is the actual speed of the air around the pellets, kind of in those interstitial spaces.
And why is that important? Because that's an interesting distinction.
It's important because that is kind of what drives the regime and actual equations. So in terms of what Reynolds number you're at, which leads to what convective heat transfer coefficient you're at. And so you can, quickly get into these crazy mathematical principles.
So the difference in velocity of the air determines how efficiently, quickly, or slowly it's giving up its BTUs into the pellet, right?
Exactly.
Pressure comes into play, right? And this is what we talk about all the time, is the fact that we're pressurizing the bed to be able to get a better uniformity within that bed, so that as you're expanding that air to fill the volume.
Yes.
Because velocity is one thing, but at a certain pressure, that's why you have when we talk about standard airflow versus actual airflow, standard airflow is at a certain pressure, right? So we're looking at this at a specific pressure level, which is why the type of blower that you're using comes into play, and why it's important, right? Because you want to have a pressurized bed so that you're not going into a vacuum at a certain point in your hopper where all of a sudden now it's just trying to escape and you're actually starting to lose heat before you even get out of the hopper.
Because pressure in a way is a way of measuring quantity. If you think about it, the pressure in this room, if we up the pressure, that would mean that there's more air in here. It's pressing out essentially. And so we need some pressure in our bed to fill those spaces. And they're tiny little spaces between the resin, But we have to fill it up because, as Greg was saying, if you have the velocity but you don't have the pressure, you're not going to get the same interactions around the resin that you think you're getting. And so that's where pressure becomes important, which has a lot to do with bed size, and it has a lot to do with some of your hopper geometry specs. What is your diameter? What is your height? Obviously, we have to follow certain L/D to get proper resin flow, but you don't want to utilize that and then compromise your airflows.
Right, and I think one of the views you have is looking down from the top and seeing the
dispersion,
which was interesting too, and probably Dana back at the studio can put one of those views up. But can you just explain it to people what that shows?
Yes. So in some of our simulation studies, especially on ours, we've been able to see really good uniformity, and we think that a lot of that has to do with the hopper construction decisions we're making. And so what that creates is you get this nice, consistent velocity from the inner tube boundary to the wall, which is going to put all of the resin under the same conditions, no matter where it's flowing in the path, because that is just going to be random. And the key is that you want that throughout the entire bed. And so you want that even all the way down right at the beginning where your diffuser bell or cone is going to be. That is kind of the starting point. If you have an imbalance there, you're going to have an imbalance throughout the rest of the bed. Because at some point, right when you click on, the air, if it's moving and if there's a bias to one side or one location, you're going to start the thermodynamic process there a little bit sooner than you're starting the other side, and then that becomes this this imbalance throughout the system,
and it just follows
and
through the whole process.
Some of your images, I think Dana can put up ours, but some of your images also show what happens when people make some changes.
Some imbalance processes.
The imbalance, and that imbalance basically is going to mean that you don't have the same results. From the middle to the side, you're going to get inconsistent drying.
Yes. You want, essentially what you want in your hopper construction geometry is you want the resin at all points to be under the same conditions. Now, those conditions are going to change based on vertically where you are in the hopper, but you want horizontally and radially it to be very consistent.
Because if it's all flowing consistently down, then that level will be get to the next conditions as it moves down.
Exactly. Right? And when you create inconsistent radial air conditions, you're going to get inconsistent resin outputs. And so then it's just going to come up to, when did you take your sample? You might get a good shot and then a bad shot because of how because of how it came out.
And you do see different side to side sometimes.
Sometimes, and a lot of times you'll see differences. inside to outside, based on some bell constructions we've looked at. Like if you shoot too much air down and you don't get it out to the sidewalls and going up, you can basically get, some inner heat and it doesn't reach the sidewalls, the side cones, what we're shooting for. And like we were saying, there's a million different levers that you can pull on how you can get there. Some of them are dictated by the physics of it all. We can't just melt the plastic, but there are decisions that you can make along the way to get to that, for better or for worse,
So
or
you can adjust in
more
process,
more efficiently or less efficiently.
You get to the world of nylons, for example. It is nylon's like a sponge and it absorbs almost to infinity. That's the real world, because most of the custom processors don't know what they're going to be molding.
Well, because like us, they're always trying to make their product better for their customers.